Hi guys, welcome back. So in the last video, we talked about some of the effects caused by neutron damage and how that affects the reactor pressure vessel's ability to withstand pressurized thermal shock. And that's for the reactor pressure vessel. But now we want to move back to our fuel, and we want to discuss what happens when there's a temperature differentials. So we have already discussed that due to the temperature differential in a fuel pellet. So what do I mean by that? In the center it's really hot, and the outside it's relatively cool. Well, this relatively cool is about 300 degrees C. By our standards it's hot, but compared to the center of the fuel pellet, it's about 1000 plus degrees C. This is cool compared to the outside. And because there's this steep temperature gradient, it causes the fuel to crack. And we're also saying that we are concerned with the thermal conductivity of the fuel because we don't want the central portion to be so hot that it starts to melt. And sometimes, well, melting does reoccur. Yeah, melting does occur sometimes, and we can see extensive recrystallization of the fuel in the center of the pellet. However, we don't just have that. Even if melting does not occur, depending on the temperature profile of the fuel microstructure will also start to change due to this temperature gradient we see here. So this video, we want to discuss more about the microstructure changes that are due to this temperature profile. And what affects this temperature profile? So factors affecting temperature profile. Well, one of these things is the thermal conductivity. We call it K. If you look at Fourier's law, conductivity is often written as K. And of course, the heat generation within the pellet. Alright, so there are two kinds of reactors we can broadly classify by the neutron spectrum. So by the neutron spectrum, we have a thermal spectrum and we have a fast spectrum. Thermal means that there's moderation happening, meaning to say that the neutrons are slowed down to roughly 0.025 eV. Oh, thermals here. Or whatever the energy of the surrounding fuel is, or the energy of the surrounding medium is. Fast is about 1 MeV, as was discussed before. So reactors can be classified into thermal reactors, where the neutron spectrum is like this, or fast reactor, where the average neutron energies are like this. Okay? So, for thermal reactors, neutrons are often slowed down from 1 eV to less than 0.07 eV. So, when I'm talking about this is 298 Kelvin roughly. That's room temperature. But because we have higher temperatures here, the neutrons may actually be slowed down to temperatures or energy slightly higher than this, and average energy higher than this. And after all, it's a spectrum, so do take note of that. So let's try and talk about this process. So for fast neutrons, they love to zip all over the place. They love to zip all over the place. And let's assume that in a reactor pellet, they're generated equally in the volume of the reactor pellet. So fast neutrons like to fly all over the place. Why? Because the scattering cross-section for them is pretty small the faster you go. That's the thing you can get from NNDC. So faster, means the scattering cross-section decreases. That's the usual trend. So they love to zip around to do some inelastic scattering in the fuel. If you're not sure what inelastic scattering is, it just means that when the neutron hits the nucleus, it doesn't just scatter off and then the nucleus comes here. For inelastic scattering, the nucleus has been promoted to an excited state. Okay, so the neutron deposits energy into the nucleus to promote it to an excited state. And of course, it imparts kinetic energy to it. Excuse me. It imparts kinetic energy to this nucleus. So, when it's in an excited state, the nucleus will like to de-excite itself and release a gamma ray. So that is what it means by inelastic scattering. Okay? So, when we have this fuel pellet, it is surrounded by cladding and water. So, when it hits the water, okay, so this is a thermal reactor. So when it hits the water, what does the neutron do? Well, water is what we call a moderator. And its main job is to slow neutrons down. So of course the water is a coolant that it's supposed to bring heat away, but in a light water reactor, the water also serves a dual purpose and is meant to slow down the neutrons. So when the when the fast neutron escapes the fuel, it becomes thermalized and then it goes back. However, this time when the neutrons go back, the cross-section increases. So, excuse me, yep. When thermalized, the cross-section increases. What kind of cross-section? N gamma and N fission increases. So the N gamma reaction, the capture reaction, is very important, especially for the uranium-238. And N fission reaction is important for the uranium-235. But in general, when the neutron slows down, N gamma reaction for any element, not just uranium-238, it can be zirconium, it can be for hydrogen, the cross-section for absorption and releasing of the gamma ray increase dramatically. So when thermal neutrons diffuse from the water back to the pellet, most of them will tend to get absorbed. The neutrons, the thermal neutrons, will be absorbed at the surface. So this is surface. Okay, the surface of the fuel pellet will experience a higher neutron flux. Why? Because before the neutrons make it to the center of the fuel pellet, they are absorbed, either through an N gamma reaction or N fission. But most of the thermal neutrons will be absorbed at the surface of the fuel pellet. Meaning to say that the fuel consumption rate and the heat generation rate near the center is lower. And that means for our temperature profile, okay, for our temperature profile, maybe, okay, the center is still the hottest, but maybe it will not be as hot as compared to a fuel pellet that has a very even kind of heat generation. So let's do a thermal. So the thermal spectrum likes to fission, and all the heat generation will likely be at the surfaces, the outer part. So Well, yeah, that may be another reason why you want to create small fuel pellets. You don't just want to decrease the temperature gradient, you want to make sure enough neutrons actually reach the center of the fuel so that there's enough fission happening. Otherwise, the outside will be burned, so-called, at a very high efficiency, while the center is relatively not so well burnt. That's another point of discussion. Now, the result for this, excuse me, the result for this is that a microstructure evolution by temperature is relatively uninteresting compared to a fast reactor. You may have sintering and some grain growth in the center of the pellet, but nothing as dramatic as a fast reactor. So what is sintering? Sintering means that when you have very small particles and you heat them up, they will join up into a bigger particle. That's what sintering means. And grain growth is a similar concept. So in the fuel we have many grains, some big and some small. So when there's heat, okay, the small grains, the fuel experiences recrystallization, and the small grains, the material from the small grains, will diffuse into materials with larger grains. So as a result, the larger grains over here will grow bigger, and the smaller grains will shrink. And the overall effect is that in the center of this fuel pellet, you will experience this grain growth phenomenon. Okay, grain growth. Why? Because of thermodynamics, a larger grain is kind of more thermodynamically stable than many small grains. And when you give the thermal energy for it to, for it to overcome the activation energy barrier, then the grains will start to grow. Now in a fast reactor, it operates almost exclusively on 1 MeV neutrons, right? So let's do the fast reactor. It operates almost exclusively on the 1 MeV neutron. So the thermalization effect I have spent some time discussing in the last 10 minutes or 5 to 10 minutes, that doesn't happen. So no thermalization. As a result, the neutron flux in this fuel pellet is roughly constant and not dependent on depth. So for a thermal reactor, more neutron flux can be found on the outside of the pellet as compared to the center. But for a fast reactor, this neutron flux is relatively constant. So what does it mean for the heat generation rate? The heat generation rate is probably the same throughout the fuel, but as compared to a thermal reactor, most of the heat generation is at the surface of the fuel pellet. Here is more or less the same throughout the whole fuel pellet. And what does it mean? We have a steep temperature gradient in the center of the fuel. Meaning to say that the center of a fuel for the fast reactor is hotter than the center of the fuel pellet for a thermal reactor, which is kind of counterintuitive if you were to look at the name. You'll think that thermal, it means hotter. Not necessarily. The fast reactor fuel pellet is hotter at the center. Okay? So we are talking about a very steep temperature gradient. So steep that at the center of this pellet, temperature can reach as high as 1600 degrees C. And slightly outside, okay, we have a temperature slightly decreased, 1300 degrees C. So temperature will drop as it goes outside. but at the center the temperature is very high and the temperature gradient is also very high. And at such temperatures, the solid does start to, evaporate. Well, not exactly evaporate completely, but just as how water, water below its boiling point, some of it escapes as water vapor. Correct? So below boiling point, sometimes water can exist as a water vapor, and this is due to its vapor pressure that it exerts. A solid can do the same thing. Yeah, the solid can do the same thing under high temperature, but below the boiling point, so to speak. But of course, this vapor pressure is much lower than the water. Okay, so what happens? And let's say you have a pore towards in the center of the fuel pellet, or towards the central region. So this is the hot side, which is the 1600 degrees C, and this is the cold side, which is about 1000 to 1300 degrees C. So what happens here? Well, there's a little bit more evaporation happening on the hot side. So there is some vaporization of this uranium oxide at the hot side here. And when this vapor will diffuse in the pore, so this is a pore, it diffuses in the pore and then it meets a colder temperature, this 1000 degrees. Then you'll start to deposit. So this side will get eaten up, and this side will get deposited. Over time, more of this side will get eaten up, and more of this side will get deposited. So in effect, the pore moves towards the hotter region. Alright? So when many pores start to migrate to the center of the fast reactor pellet will start to have a central void. So have a central void. Now you might ask, are we running out of pores after this process happens? Because there are only a certain number of pores in the material, and if all of them migrate to the central void, will there be any pores left? Oh yes, there are. Why? Because when there are cracks in the fuel, this same process can happen, and the pore can start to grow from the crack. Okay, when the pore grows from the crack, it can butt out and you'll start traveling towards the center. Okay, so let's say again you have this fuel pellet, you have the central void, you have some cracks in the fuel, and these cracks will start to emit voids which will then travel to the center. So the central void will keep growing and growing. So when the pores migrate towards the center, okay, when the pores migrate towards the central void, so this is the central void. I'm enlarging this part. Okay, when the pores migrate towards the central void, they tend to leave a kind of a trail behind them. So in the fuel microstructure, you'll probably see something like this. You see? Yeah. So these trails can be seen under a microscope, and with many of the trails tracing towards the center, you have something like this. Okay? So you have a central void, what you have is a central void with many of the pores that are going to the center, and you can look at the trails of them. And this is what we call columnar grain, because it looks as if going towards the center there are many columns that are pointing towards the center, so they call it columnar grains. Or okay, they call it columnar grains. And during of course, because of the high temperature involved, which is 1600 degrees C, we also have a grain growth process that happens. So there is a pore migration and a grain growth process that happens towards the center, and this is where we have columnar grains, or we also call it the columnar region. So the central part is known as the columnar region. Now just outside the columnar region, we have a temperature gradient, a region of high temperature. So we have all these columnar grains. So just outside the columnar region, we have maybe somewhere over here. So it's not quite the center, not quite the outside, just somewhere in between. We still have grain growth process because of the high temperature, but no more pore migration because the temperature gradient is not high enough. So this is what we call, just outside the columnar region, we call it the equiaxed region. Now outside the equiaxed region, that means on the surface, there is a minimal grain growth process, which constitutes the outer ring of the fuel pellet. Okay, so these are the major thermally driven processes inside the fuel pellet. Now, of course, as explained before, just a side note, yeah, radiation. Okay, this is not a thermal process, but radiation will, of course, create vacancy and interstitial between here, inside between each grain. And of course, just like what we have in our FCC structure before, voids will start to accumulate at the grain boundary. And here we will have what we call intergranular porosity. So this happens all throughout all three regions, the outer region, the equiaxed region, and even the columnar region. All this will happen because of the Frankel pairs that are being generated. But in the columnar region, of course, the diffusion rate's a lot faster. So because of the high temperature, so maybe you'll probably see more of the bigger grains, and you also see the porosity between the grains. That's what's called intergranular porosity. So most of this video is from chapter 14 of Professor Donald Olander's book. The link is shown below. Okay, so that's all I have for you in this video. Yeah, so thanks for watching. I'll see you guys again. Bye bye.